Okay, so as promised, we're going to spend this hour just solving tutorial questions. So we covered a lot of material the last couple of days, especially the amplitude modulation knowledge. So it'd be nice to go ahead and do some sample problems. Once I do that, I'll cover the rest of amplitude modulation today to finish things off. So we're going to start off with a very simple problem. Again, it's signals and systems review, but this talks about distortionless transmission, which we covered a little bit in theory a couple weeks ago, but I actually didn't solve the question. So it'd be nice to actually see that in practice. Okay. So we've got a communication channel with the following transfer function. So it looks a little unorthodox, but it's actually quite. We'll deal with that as we go. So it's h of omega. So we're going to deal with this in omega. I'm going to have questions that will switch between f and omega, so you have practice. But when it comes to the midterm, you can choose whichever notation you're most comfortable with. Okay. So we have a communication channel h of omega that is of so, and then the first question says we've got some signal with some frequency spectrum. We don't know what it is, but we know that it's some signal with some frequency spectrum. So what we need to do is we have to figure out exactly what the output would look like. So when you take a look at this communication channel, what the output would look like when you send a signal through this channel. Okay, so we're going to figure that out first. Okay, so that's actually quite easy to figure out. So actually, let me view. Sorry, I like to have some colors. Okay, that's good. Okay, so so we have some arbitrary signal. We don't know what it is, but we're going to put it through some communication channel. Okay, and then the output is in time domain. So if you remember from signals and systems, the output is just the convolution of the input and the channel, right? So actually this is h of t. Okay. Equivalently, if we went to frequency domain, it's just multiplying the two things together. Okay, so that's what we're looking for. So we want this in terms of frequency domain, if I recall the fine expression for the output spectrum. Yep, output spectrum. Okay, so h is from the question here. This is equal to, what was it? It was 1 plus 2 alpha cos omega t, and then e to the minus j omega t. Okay, that's cool. All right. Okay. So, yep. All right. Okay. All right. So we have this. All you have to do is just take x and just multiply by this guy over here. So you just have to bring it over there and multiply, which is very nice. Okay, that's cool. So x, and then multiply by 1 plus 2 alpha. Okay. This is nice and all that, but we can simplify this a little more. Actually, I'm going to show you what the time domain expression looks like, because it'll actually look a lot nicer than what it looks here. Okay, so if you remember from Euler's formula, if you remember cosine x is equal to what? It's half e to the jx, right, plus half e to the minus jx. Okay, that's very nice. So in this case, x would be omega t, all right? So in this case, let me just write this out. Let me just simplify this a little more. Notice that you have a 2 here and then a factor of half. That'll cancel, but let me just write it out to be explicit. Okay, e to the, okay. So we see here that this factor of 2 cancels out with these. That's nice, okay? And then we can also express this. So we have 1 plus alpha e to the j omega t plus alpha e to the minus j omega t. And then we can multiply this by e to the minus j omega t. Okay. Now, what we can do next is we can take this and we can carry it inside, all right? So remember, when you take 2 exponentials and multiply them together, it's the same thing as what? Just adding the exponents together, okay? So when you actually write this out, okay, this becomes x of, and I'm just going to expand this. I'm going to skip a couple steps. So we have x and then times 1 here, e to the minus j omega t, okay, plus alpha x. And then when we have e to the j omega t and then times e to the minus j omega t, that's equal to what? Just equal to 1, right? Because you have e to the a and then times e to the minus a. When you multiply them out, the exponents add up, which is e to the 0, which is 1, right? So that's fine. And then plus alpha x j omega e to the minus j 2t. Okay, great. Now, so this is what it looks like in frequency domain. We can go back in time domain. If you recall, there's this shifting property, right? If you delay by some time instance, t naught, and then if you take the Fourier transform of this, it's just the regular Fourier transform and then e to the minus j omega t naught, right? If you remember this property here, this is what we call the time shifting property. So if you examine each of these exponents here, you'll notice that each of them have a time shift, right? So this is t naught here, this is t naught here, and then this is just by itself. So if I wanted to write this out in time domain, this is equal to what? So we'll write this out in order. So this is alpha x of t plus x of t minus t, right? Plus alpha x of t minus 2t. So where these all come from, so let me see. So this guy is over here, right? This guy is over here, and this guy is over here. Okay? No questions here? Are we good here? Right, so I just multiply the two things together because that's what convolution is in frequency domain. You just multiply the two signals, and then you expand out the exponential, use the cosine formula for Euler's, and then you have to recall that there's a time shifting property from going, when you shift in time, you multiply by a complex exponential in frequency domain, and this is what we get. Okay, that's very nice. Nice little warm up there. Okay? Oh, okay, it looks like I did part B as well. Okay, so if you take a look at part B, from the above expression, show that the output signal has the form. Okay, I guess I already did that. Okay, so this would be A, okay? This would be B. So I had 2 and 1. That's actually quite nice. Okay, all right, so let's take a look at part C. What are the conditions for distortionless transmission? Okay, so C. Okay, remember what the conditions were. Let's remember way back. So if you remember what the conditions for distortionless transmission were, the magnitude is constant. In this case, we're taking a look at all of the entire frequencies, right? So the frequency spectrum is constant for all frequencies, and the phase is linear. Okay, so that's what the criteria was. So the magnitude is constant for all frequencies. Sorry. Okay, right? And the phase is linear. Okay. All right, so this is what we had before. This was 1 plus, not 2, but alpha. Okay, so if you take a look, this would be the magnitude, right? And this is here is the phase. So we can clearly see here that the magnitude is that the phase is linear, right? Because this would be the phase is equal to just minus t. Not minus t, minus omega t. And remember, for something to be linear, you have to make sure that the variable is just omega by itself. Or if you were to take the derivative of this, it's just equal to a constant. So this is fine. Okay. However, this one, it's not constant, because if I substituted different frequencies, if I substituted 0 or pi over 2 or whatever frequency you want, I'm going to get a different magnitude. Okay, so in this case, the channel would be distortion because it's not the constant magnitude, or it's not a constant magnitude over all frequencies. All right, so the magnitude is this. So if you recall, so 1 plus. Okay, so not constant over all frequencies. Okay, because if I substituted h of 0, right, what am I going to get? I'm going to get 1 plus 2 alpha, right? Okay, if I substituted pi over 2, I'm going to get 1, right? So this is not equal to each other because this should be constant over all frequencies. Therefore, distortionless. And not distortion, this has distortion. Practically, you would only consider something to be distortionless within a range of frequencies, but in this case, this question asks you for the ideal case. You want to check all frequencies to see if it's constant. In this case, it's not. So therefore, this has distortion. All right? Okay? Make sense? All right. The next question asks you if we let x equal rect t over tau, okay? They want you to sketch y of t when alpha is a half and when tau is 2t over 3. Okay? So if you remember what the expression was, we had alpha x of t plus, and then it was x of t minus t here, right? And plus alpha x of t minus 2t. Okay, so this is actually really simple to do. This is like a joke, all right? So in this case, we have tau is equal to 2t over 3. So in this case, rect of t over 2t over 3 is equal to what? So it's a rectangular function which spans between minus to plus t over 3, right? Because you want to figure out where the halfway point is. So in this case, it simply looks like this. All right, so this is 1, and this is minus t over 3, and this is t over 3 over here. Okay? That's great. So all you have to do is just take this, and then you just have to draw this 3 times, okay? One, which is just by itself with a scalar factor of a half, and then one you're going to shift it over to the right by factor of t, and then you're going to shift it over by twice as much, and then you're going to sketch that by half again. So that's actually quite simple to do. So we have the first one. Oopsie, can't draw, or can't write rather. Okay, so it's scaled by a half. Okay, so this is the first one. Okay. Then the next one we draw over here, so we're going by t, and then this spans by t over 3. There's a radius of t over 3. So when you go t over 3 to the left of t, you get 2t over 3. Okay, and then when you go to the right, it's 4t over 3, and then it's scaled by just 1. So okay, whatever. Okay, good. Okay, and the last one, we have one that's 2t, okay, and then it's also scaled by a half, and then this spans by plus minus t over 3. So this becomes 5t over 3 and 7t over 3. Yeah, that's it. Okay, so the red is over here, orange is over here, and finally, I guess the green is over here. And that's it. All right? Okay, makes sense, right? Any questions here? Just want to start you off with an easy one before I go and do something a little more difficult. Okay, just a warm up. All right, good. Let's keep going. I've got maybe about 3 or 4 more questions, then we'll take a break, and then I'll actually go back to the theory. Okay, so here's the next question, guys. Again, these will be posted online, so if you're frantically trying to write, it's okay. I'll post these online. So I'd like you to pay attention, but if you want to write something down, then by all means go ahead. I'm not going to stop you from doing that, but it would be nice. Okay, next question here. So this is a double sideband suppressed carrier question. So here's a message signal which consists of a sum of 2 cosines, okay? So we have one frequency which is centered at 100 hertz. I'm going to do this question in hertz this time, not omega. So I'm going to flip back and forth so we get some practice here, all right? And then the next frequency, we have it as 300 hertz. Okay, so the above signal is modulated with a carrier frequency of 1 kilohertz or 1,000 hertz. So this is the carrier frequency. So we're going to shift all the frequencies plus minus 1,000 hertz, okay? All right, so what I'll do is I'm going to change this to F instead of omega. I want to do some practice here. So first, we're going to sketch the DSB-SC signal, and then we're going to figure out what the upper sideband spectrum is and what the corresponding upper sideband signal is. Okay, so just a quick refresher. This is from last week, okay? So a double sideband suppressed carrier signal, the modulated signal, it's simply taking your message and multiplying it by some cosine that's modulated at some frequency, okay? So in this case here, this is 1,000 hertz, All right, so therefore, we have m of t. Yeah, that's fine. So m of t and then cosine of 2 pi times 1,000 hertz. Okay, so if you remember what the frequency spectrum looked like, okay, if you remember what the Fourier transform was, so what you're doing is you're taking this signal and you're shifting to the left and to the right by whatever the carrier frequency is, and you have to make sure that you multiply each of those copies by a half. It's from the multiplication in time is convolution in frequency, all right? So in this case, we get half m f minus 1,000, okay, plus half m f plus 1,000, okay? So we need to figure out what the original spectrum is first, and then we're going to shift back and forth. So what's the actual spectrum? So m of t is equal to, what was it? It was this guy. So it was cos 2 and then, sorry, 103. So cos 2 pi times 100 plus cos 2 pi times 300. Okay, so if you remember what the Fourier transform for this was, okay, so this is just 2 impulses, right? 2 impulses that are just scaled by a half, I think. Actually, yeah, I'm pretty sure it's scaled by a half. Let me just double check. Yep. Well, one moment. Okay, that's fine. Oops. You good? Okay. Okay. I'm trying to remember. 2 pi. Yeah, so it should be a half. That's fine. So we have actually 2. No, sorry, it's not a half. It's just an impulse by itself. Oh, my apologies. So, okay. So remember, when you take the Fourier transform of this guy, you're going to have 2 impulses that are plus minus 100, right? So you're going to have delta f minus 100 plus delta f plus 100. Okay, so that's this. So that's this one over here, and then we have another pair, plus delta f minus 300, and then plus. Okay, so the original spectrum looks like this. So we have minus 300, minus 100. So this is not to scale. Actually, let me just draw this again. So 1, 2, 3. So if this is 300, this is minus 100, 100, 300. And then we just have impulses that are just like that. Okay? Okay? Pretty sure it's just one. Yeah. Pretty sure it's just one. That's good. Okay, so this is what the original spectrum looks like. Now what you need to do is you have to, sorry, yes?
For the impulse at 300.
Yeah.
Is the amplitude, is that supposed to be 2?
Is it 2? Oh, sorry, yeah. So this would be 2, and then this is 2, and then 2. Thank you. Okay, so in this case, we'll get rid of this. If I make a mistake, you gotta let me know sooner, or I'm gonna carry on and I'm gonna look like an asshole. So. Okay, we're in agreement now, right? Okay, good. Yes?
Doesn't the amplitude also, because you know it's divided by 2 when you Fourier transform it?
Yeah.
There's 2 pi, right? So
Yeah.
wouldn't the amplitude be pi?
Oh, I'm doing it in terms of f, not omega. When you do it by f, you multiply by 2 pi, right? Actually, it would be, sorry, you know what? It's actually scaled by a half here. It's actually scaled by half, and when you go to omega, it's multiplied by pi. Yeah, sorry, so it's actually a half here. So it's half, half. Sorry, I keep forgetting. Okay, so in f, it's a half, but when you go to omega, it's pi. Yeah, so what's happening here, yeah, because remember, when you're doing the Euler's formula, you have a 1/2 e to the power, 1/2 e to the power, and then the impulses get multiplied by 2 pi. So 2 pi divided by 2 would be pi then. Okay? So, you know, I'll write that down just for practice. Okay, so we have this, so this is pi, pi. Okay, so if you were to do m of omega, this becomes pi, and then this, instead of 100, this becomes 200 pi, right? And then plus, and this becomes 2 pi here. I'm just doing this for practice, but honestly, on the midterm, you can do it however you want. If you're comfortable with f, go ahead and do it in f. If you're comfortable in omega, then you do it in omega, whatever you want. It's just for the sake of a convenience. Some people like to do it in omega, some people like to do it in f. Okay, so that's totally fine. So yeah, this actually, I forgot. So this is actually scaled by half. So this is a half here, and then this is 1. Okay. All right, so there's either you can either do it this way or you can do it this way. It's up to you. Okay, so now that we have that, what we need to do now is we have to modulate by 1,000. So all you have to do is you just have to take this spectrum, copy it to the right over by 1,000, copy it to the left over by 1,000, and make sure you scale the amplitudes by 1/2. Okay, so it's basically going to look like this now. It's going to look like this, and then what's going to happen is you're going to have two copies, one to the left, one to the right. So take all of these frequencies and add them by 1,000. So -3 becomes 7, okay? -100 becomes 9. We have our frequency, carrier frequency, and then we have 1,100 and then 1,300. Okay, and then you have to make sure that all these are scaled by an additional half. So we're going to have a half here and then 1/4. So it's going to look like this. 1, 2, 3, 4. And then you copy the same thing on the other side. So you're just going to take the negatives and positives, they become negatives. So 13, 100, so the center is 1,000, 900, 700, so 1, 2, 3, 4. Okay, and that's finally what you get. So that would be the double sideband suppressed carrier spectrum. So you take the original, shift left and right by the carrier frequency, and then make sure you scale the amplitudes by 1/2, because that's what the property asks. Okay? Okay, next question. It says, obtain the upper sideband spectrum. Okay, so that's actually quite easy to do. So remember, we can split it right at the carrier frequency, we would split it down the middle. Any frequencies that are beyond the carrier, so in this case, this side here is the upper sideband, right here as well, upper sideband. Okay, and this here would be the lower sideband. So if you just wanted the upper sideband, what you do is you just take a look at the upper sideband by itself and you don't consider the lower sideband. So the upper sideband would just be these two impulses, okay? So the upper sideband, okay, would be just these two impulses. So we get half delta F minus 1,100. Not 1,100, it's 1/4, sorry. So 1,100 is 1/4. Okay, and then you have a half at the 1,300s. Okay, sorry, it's a little unclear there. 1,300. Okay, so then this is B, and then part C is to figure out what the time domain signal is. Okay, well, if you recall, here, remember, this collection of two impulses would give you a cosine. Okay, so this becomes half cosine 2 pi 1100t, and then plus just cos, 2 pi times 1,300. Okay, so this would just be these two guys over here, right? And then this would be this guy over here. So you want to figure out what the equivalent time domain is. So remember, when you are taking a Fourier transform of cosine, you get two impulses. So I'm just going the opposite way. So I have two impulses defined at plus minus 1,100. So if you collect those all together, take the inverse, you get a cosine. And make sure you multiply by 2. And then you do the same thing here for the other side. You have plus minus 1,300, you get a cosine there. And that's it. Okay? So that's what you get if you wanted to figure out the upper sideband by itself. And we'll talk about single sideband transmission later on in the course, maybe in about half an hour or so. Okay? Okay, any questions here? Okay. So I'll let you guys copy that down while I queue up the next one. Okay, I'll do it in omega now because I think people are more comfortable in omega. Okay, but I wanted to do F first because it depends on what your preference, but I want to make sure you're comfortable in both. Oh, come on. Give me black. Very good. Okay. All right, so we're going to take a look at AM modulation or double sideband large carrier modulation. So here are some. So we have this signal. This is the output signal of an AM modulator is this. So what this is saying here is that this is not the message signal. This is the modulated version after you perform AM transmission. So this is the modulated output. This is what we see here. Okay. So Determine the modulating, we'll call this the message signal. So given this modulated signal, we want to figure out what the original message signal was, as well as what the carrier is supposed to be. Okay? Also determine the modulation index, which is mu, and then also determine the ratio, the efficiency. Right? So we got to figure out what the power in the sidebands are compared to the power of the carrier. Okay, and that's pretty fine. Okay. Let's see here. Just want to make sure I got this. All right, good. Okay, so this may not look so obvious, but if you remember what the spectrum looked like, if you actually draw out the spectrum first, it might actually help you figure things out. All right, so let's figure out what the actual spectrum is. Okay, so remember that when you have cosine in terms of omega, when you're actually finding the Fourier transform, you just multiply by pi, right? So in this case, you get 0.5 pi delta omega minus 1800 pi, right? And then 0.5 pi delta omega plus. So this is the first one, okay? Then we have the second one, 2 pi delta, and then we have omega minus 2 pi omega plus. Okay, and then finally the last one. Sorry, can't write today. Did I go full screen? I didn't go full screen. Okay, that's better. So omega, and then this is plus. Okay, so it may not look obvious now, but let's actually draw what the spectrum looks like. So we see that there's going to be 6 impulses altogether, 3 on each side of the actual, the actual axis. So we're going to have 1800 pi, 2000 pi, 2200 pi. Okay, and there's also copies on the left side in the terms of the negative values. Okay. So we see that we got pi over 2, and 2 pi is going to be up here. So we have 1 impulse here. We also have 1 impulse there. Sorry, 1 impulse here, and then same thing on this side. Okay, so if you actually look at the actual spectrum now, it's going to look a little obvious. So we can clearly see that here and here is going to be the carrier frequency, right? So this would be the carrier frequency. Okay, and then obviously these guys, these here are your message, these are the sidebands. Okay, so we can clearly see that our carrier is going to be 2000 pi. The frequency is 2000 pi. So if you remember what the actual time domain signal was, if you remember what the time domain signal was for the amplitude modulation, it was what? It was A plus m of t cosine omega ct, okay? So we know for a fact that this is going to be 2000 pi, okay? And we also see here that when you take the Fourier transform, you're multiplying by 2 pi plus. So we can clearly see that if the impulse side is 2 pi, then the carrier amplitude should be 2, right? Because when you take the Fourier transform, you just take whatever, cosine you have, you multiply by pi, and then you have an impulse. So in this case, you just have to get rid of the 2 pi, and then you're left with A is going to be equal to 2, and that would be what the carrier amplitude would be. Okay, so let me double check. Just checking to see if I got this right. Okay, good. 2 cos. Yep. Okay, so if you remember, okay, so we'll just call this A, I guess. All right. The Fourier transform of this will be pi A cosine omega plus omega c plus pi cos, A plus omega c. Okay, pi A. Okay, so when you have this relationship, we can clearly see that A is just going to be equal to 2. So our carrier is simply 2 cos 2000 pi t. Okay, now the message signal is quite obvious. We can see here that these are even, and then we've modulated by 2000 pi. So all you have to do is just take each of these frequencies and subtract by 2000, and what do you get? So your actual message signal, your message spectrum, right, is going to look like this. So it's plus, and then this is minus 200 pi, Okay? But if you remember what the spectrum was, okay, this was what? It was A pi, so I'm just going to take this guy here, copy this over. Nice thing about tablets is you can actually, copy actual pen strokes, which is great. Okay? And then this becomes plus, and then remember we have M of t cos, so this is actually modulating, so this is a double sideband suppressed carrier spectrum. So we have okay, actually, let me copy this on the bottom, because it kind of looks out of place. So let me delete this. Sorry, not delete. I wanted to undo. There we go. Let me just cut. Okay. Okay, let me get rid of this for now. This is it's gonna be a little confusing. So that's good. So this is what I have here. Okay, so this I already know. But then if you take a look at this guy, so what we have to do here is we notice that we have our spectrum, which is plus minus omega c, and then it's also scaled by a half. So if you want to figure out what the original message signal is, you just have to take each, it doesn't matter which one, just take one of these, bring it back down by 2000 pi, and then you have to multiply by 2 to get rid of this scaling factor of a half here. Okay, so the actual message signal, okay, will look like this. So it's 200 pi, 200 pi, and then there are 2 impulses, but then you have to make sure you multiply by 2. So in this case, this becomes pi. Okay, so in this case here, remember that the cosine wave, right, it has 2 impulses that are defined by plus minus omega. In this case, this is 200 pi, so our message signal is simply just cosine of 200 pi t. Okay? Does that make sense? So our carrier is cos of 2000 pi, and our message is just cos of 200 pi. Right, so that's what the property says. Okay, so that would be that. All right, so next question. B, determine modulation index. Okay, determine the modulation index. So you can use, because this is symmetric, you can use whichever definition you want. So you can use the max and min definition, or you can just use the maximum peak. I'm just going to go ahead and use the maximum peak definition because this is a symmetric. This is a symmetric signal. So, okay. So the maximum peak of this cosine wave is what? Well, it's just going to be equal to just 1, right? Because this is the largest peak that you're ever going to get. So remember, so the cosine wave, the largest value is 1, and then the carrier is 2. So our modulation index is simply 50% or 0.5. Okay. So the next question asks you to figure out what the sideband thing is, the total sideband power compared to the carrier power. All right. So PS divided by PS plus P of C. Okay. So if you remember what the power of the sideband, power of the message signal was, it's simply the time value squared over 2. And if you remember from previous class, right, if you wanted to figure out the, what was it? If you wanted to figure out what the power was for a cosine wave, right? So we had, if M of t was a cosine wave, right? The time average value was simply equal to 1/2. So in this case, if you had a constant A, this would just be A over 2. Okay? So therefore, this would just, so we have our, let me see here. So we are, our signal was cos. In this case, you'd have 1 over 2 divided by 2, which is 1 over 4. Okay? And then the power of our carrier, same thing. You just take the carrier signal, figure what the time average is, divided by 2. And in this case, it's also just, what, 1/4 as well. Actually, no, it's 2, right? So we have 2 divided by 2, and then divided by 2 again, which is just 1/2. All right? So therefore, the efficiency is 1 over 4 divided by, 1 over 4 plus 1 over 1/2. Okay, if I multiply it up and down by 4, okay, what I'll get is 1 divided by 1 plus 2, which is 1 over 3, and that's 33%. So this verifies what we talked about previously. If you just have a single tone modulation message, The maximum efficiency you'll ever get is 33%, and we verified this already through this example. Okay? All right, any questions there? Did I make a mistake? Double checker, mistake, double checker. Did I make any? Were you okay? I'm gonna denote you as my mistake checker because you seem to point out all my mistakes. So, but I'm okay here. Are we okay here? Yes. Question. I'm sorry. What was your question? In terms of the actual signal itself? Oh, well, you can see, remember that, and when you're taking a look at an amplitude modulated spectrum, you'll see here that if you were to put a horizontal mirror right at where the carrier frequency is, you'll see that there's a split reflection. Okay? So that actually is right here. So if you were to put a mirror right here, you'll see that on one side, if there's one part of the spectrum and the other side is the other part. So that frequency where if you were to place a mirror and if you see a reflection on one side and the other side, then you know that's where the carrier frequency is. Okay? So in this case, like it's right here. So think of putting a mirror right at the 2000 mark, and you see one side is one spectrum, the other side is the other, and then you see one's a mirror reflection. If you can find that point, that's where your carrier frequency is. Okay?
Why can't you take 22,000 as a curve? But that requires the modulated side.
I'm sorry?
22,000, 2200.
If you were to put, okay, then it wouldn't be symmetric because if I put one here, there's nothing on this side. You have to take a look at symmetry. You have to take a look at left and right of where that is, and then it has to be exactly the same, just mirror reflected. Okay. So if you want this to be symmetric, then you'd have to expect that there's going to be 3 other impulses on the other side of that green line, and that's not correct, right? So you have to make sure that you put a line where you take a look at the left and the right only on the positive side. Forget the negative side, but on the positive side, you see that there's a mirror reflection. If that's the case, that's where your carrier frequency is located. Okay. All right, that makes sense? All right. Okay. All right, let's see here. 4. Okay. Okay. We've got a couple more problems, okay, and then we're going to take a break, all right? But it's nice to actually see, problems where, you can actually get some practice. Okay, so we're going to do AM modulation again. So this is our message signal. So this is not a modulated signal. This is the original message signal. Okay, so this is before modulation. So consider a baseband message signal such that we have this. So we have a DC offset. We also have 2 cosine waves of 100 hertz and 200 hertz. Okay, so this is what the diagram would look like. As I talked about, when you want to do large carrier modulation, you add a DC offset and then you modulate. So this is just your standard block diagram to do that. We also, let's see here, the modulation index is mu, so we don't know what this is. This is unknown, but we do know that the carrier frequency is 10 kilohertz. That's good, okay. Compute and plot the spectrum when the modulated signal is mu is equal to 0.5. What is the efficiency? And then we'll talk about this next. This is what is known as a sufficient condition. So if you want to be able to use an envelope detector properly, you have to make sure that the index is between 0 and 1, but that might not be the case all the time. And this is a question where you can actually get an index which is greater than 1, and you can still be able to recover your signal properly, but that's a special case. Okay, so A. Compute and plot the amplitude modulated spectrum when the signal is at mu is equal to 0.5. Okay, so if you remember, so this is symmetric, so it doesn't matter which definition you use. I'm just going to use the maximum peak one. So mu is equal to MP divided by A. Okay, so we don't know what this one is. Okay, we do know that this is 0.5, and we can certainly figure that out. This is no problem. So if you take a look at this, what's the maximum height ever going to be for this signal? So remember that we can see here that the 2 cosines will meet at time index 1/200, and then both of them are going to add up to give you 2, and then you also have that DC offset, which gives you 1 more. So what will be the maximum peak? It's going to be 3, right? Yeah, 3? Good. So in this case, we know this is just 3, because at time is equal to 1/200, right? 1/200. So m of t would be equal to 3. Okay, so this is what the maximum peak is. So this is 0.5 equals 3 divided by a, and then a would just be 6, right? So all you have to do is just, do this cross multiplication, bring the a to the top, 0.5 to the bottom, and 3 divided by half is just 6. So this means our carrier amplitude will be 6 in order to make our modulation in x.5. So all I have to do now is sketch what the spectrum looks like. Okay? So if you remember what the spectrum looked like from the past, okay, let me just write this out again. Actually, I'm going to get it right here. This is good. This is very nice. Oops, I didn't want to delete, sorry. I have a habit of doing that. Let me copy. So I don't want to keep, rewriting it, right? So paste. Okay. All right. Okay. So this is what we need to sketch. So let me see here. So our message originally was 1 plus, and then we had 2 cosines. So cos of, I'll do it in pi notation this time. I think, was it 2, 100, 200? Oh, sorry, it's 2 and 4. So 2 and 4. Okay? So, okay. So if I want to figure out what the Fourier transform is, remember the Fourier transform of a constant is just an impulse, but it's multiplied by 2 pi. If you remember from signals and systems, so this becomes 2 pi, and then it's just one impulse centered at omega is equal to 0. So that's what this is over here. Okay? The next one is very simple. Remember, there are 2 impulses. This is going to be plus minus 200 pi, and then each of them are going to be scaled by pi, right? So we're going to get pi delta omega minus plus omega plus. Okay? And then we have another couple that are, it's going to be pi, and then we have one at 400, and then another at minus 400. Okay. So this is what the original message spectrum looks like. So that's what this is here. Now all we need to do is we just have to take this and plug it into our amplitude modulated signal. In this case here, we know that our carrier wave, the amplitude is going to be 6. So we know that already. So we just have to sketch this out. So if you don't mind, I'm just going to jump right to the answer. Okay? So we know that our carrier frequency is centered at 10 kilohertz. This means that omega c would be 20,000 pi, right? Because if it's 10 kilohertz in omega, you multiply by 2 pi, so that's 20,000 pi, right? So we know that it's going to be centered at 20,000 pi. Obviously not to scale, so if you were to take a ruler, it's not going to work, okay? And we know that the carrier frequency, and not the carrier, the carrier amplitude is 6. So this is 6, we're going to make 6 pi all the way up here. So 1 here and 1 here. That's great. Okay. So let's see here. So we have 2 pi's, and then also what's going to happen is that because when you're shifting, notice that we have an impulse that is defined at delta omega, all right? So if we were to shift this by 2000 pi, what's going to happen is that you're going to have this and then added this on top of the 6 because you have this 2 pi here. So this actually becomes 6 plus 2 pi, okay, because of this guy here. Because remember, when you're shifting, when you shift, right, we're going to have 2 pi delta omega minus 20,000 pi, right, and plus delta omega plus. Okay, so not only will you have the impulses from the carrier, you're also going to have the impulses from the message signal. You have one that's already defined at 0. So when you shift over, you're going to have another one, which is 20,000 pi. So this is from the message. So you have 2 on top. So this becomes 8 pi. Okay. And then what's going to happen after? Actually, no, I have to divide by 2. So it's actually 7 pi, not 8. Sorry. So this is actually 7 pi. Okay, because remember, what you're doing is you are dividing by 2, because that's what the message tells you here. You're dividing everything by 2 here. So we have 6 pi, 6 plus 1, which is 7 pi. And then all you have to do is you just have to take these guys and just shift them over by 20,000. So there's going to be 2 of those. Okay, so let's see. So we have 19,800. Okay, and we have 19,600. And then we have 202 and 204. Okay, so let me see here. So we have 204, and then 202, and then we have 19,800, and then 19,600. So then, let me see here. So all these will get, oh, so this is a pi here. All these get multiplied by pi over 2. So 1, 2, 3, 4, 2, 3, 4. Okay. So that's what it would look like, and this is in terms of omega. All right. Does that make sense? Okay, remember, you have the 6 pi from the carrier, and because you have an impulse that's already defined at omega is equal to 0, when you do your plus minus your carrier, you're going to have an additional impulse that is centered at the carrier frequency. So when you take your message, you have to divide by 2, so you get a pi. So you have 6 pi plus pi is 7 pi. So that's why you get those 2 impulses. And then these 4 are defined pretty much from the message here. We're just doing plus minus 20,000 pi, and that's what we get. Okay? And that would be what the spectrum looks like. All right, yes? Yeah, that's right. So what what will happen is that if you did it in frequency, you'd have to divide by half. So instead of it being pi, it'd be 1 over 2. Right? Because remember, so if you took the Fourier transform of an impulse, not an impulse, it would be if it was e to the power, you would just get a delta, right? But because cosine is half e to the power plus half, you have that extra half there. So that's why you have half delta plus half delta. Okay? So in frequency, you multiply by half. In omega, you multiply by pi. Okay? Does that make sense here? Okay, so I'm gonna, let's see here. What's coming? Okay, so let me see. So I'm just gonna do B and C here, and then I think that's about it. And I'll save the nonlinear stuff for next class, I think. Actually, maybe I should do it. Let me just double check. See how much time I got. Oh, yeah, I'm gonna do that quickly, sure. Okay, so in part B. What is the efficiency of the amplitude modulated signal when mu is equal to 0.5? So we have to find the power of the sidebands. We have to also find the power of the carrier as well. Okay? All right, so let's do that. So this is our message signal from before. Okay, so this we already know. Okay, so the power of this is just a half. Power of this is also just a half. Okay, but what about this guy? How does this actually work? So the power of a constant, how does that actually work? Well, I'm going to show you a little proof, and then you'll see, you'll agree with me that it's just going to be that value squared. Okay, so if you want to figure out what the time average is, you remember what the equation was. You just take the limit as some period approaches infinity, 1 over t, and then you want to go from t over 2 to t over 2 of the actual message squared. Okay, so this is what the definition was. Okay, so I'm going to take a leap of faith here. So this is what I need to find the power of, this guy here. Okay, so this is what my message is, roughly. So would you agree with me that this would simply be a rect function where the width is very, very, very infinitely large, right? So you'd think that this is the same thing as taking a rectangular impulse and making the tau very, very large, right? It's pretty much the same thing. You're just making it go towards infinity, right? So this would be the same thing as pretty much the same thing, right? Because if you remember what the rectangular pulse looked like, this is tau over 2 and this is tau over 2, rect of t over tau. Okay? So if I were to take this value of tau controls the width of the pulse. If I make it infinitely large, you would think of that as just being a constant value that's pretty much spanning over the entire time domain. Okay? So why don't I use this and exploit that into this equation here. So this becomes, so in this case here, so we have t, right? So in this, actually what I can do is now is I can change this to tau if you want, but because I'm doing it over a period of time, right? So you can actually make this, I can change this to tau and it's still going to be the same thing. And I'm going to square this. Also, this should be dt, sorry. I'm doing it in respect to t. Okay. Okay. So this is defined between minus tau over 2 to tau over 2. So in that case, the height is just going to be 1. and it's also just going to be squared. So actually, you can just replace this with right? Because it's just, you know, it's only defined between here and here. It's just 1, and then it's just squared because it's only defined between, you know, this bound, and then it's just 1. If you square it, it just becomes 1. And then when you integrate this, what does this become? This becomes, you know, it's just x and then tau over 2, so this becomes tau. When you actually evaluate this, it cancels out, so you just get 1. Okay? So it's just equal to 1. So in general, if you had a rectangular pulse of height a, then the power will be simply a squared. Okay, that's in general. But anyway, we can just do it like that. So that would be the power of that single flat line. Okay, so therefore, the total power, okay, is simply 1 plus a half plus a half. Okay, and then you have to actually, so it's actually 1, but then you have to, okay, but then you also have to divide by 2, right? Because if you want the time domain average, right, it has to be 1 over 2. Sorry, so this is actually a half here. So this is from the 1, this is from the cosine, you know, 200 pi, and this is from the cosine 400 pi. Okay, so there we go there. So that would be the total power, which is actually 3 over 2. So this would be the total power for the sidebands. So this is P of S, okay? P of C is very simple. It's just 6 squared divided by 2, okay? So in this way it'd be 18. So whenever you have a cosine wave, you just take the amplitude squared and divide it by 2. So the carrier is equal to 6, right? So let me just, yep, so then you got 18. So therefore, the efficiency is going to be 3 over 2 divided by 3 over 2 plus 18. And then if I multiply it up and down by 2, this becomes 3 divided by 3 plus 36, which is 3 over 39, and 1 over 11, which is pretty shitty, actually. It's not a very good efficiency. Whatever that is. I think it's like 9%. That's actually pretty bad. Okay. All right. Actually, I don't have time to do the last one. So let me just do this last problem quickly. We'll take a break, and then we'll come back and finish off the theory. So the last question was, let me see here. C squared, yeah, C squared divided by 2, yeah. Let me just double check. Oh, I think I made a mistake there. Actually, so C squared is actually 2, so this is actually 4 divided by 2 divided by 2, which is actually a half. Oh, wow. Okay, 4 divided by 1. So I'm just double checking my work here. So you have 1, 1. Okay, but anyway. I'll have to do that later. Okay, so you learned in class that in order to use the envelope detector, the sufficient conditions be 0 and 1, but it's not always necessary. For the signal M of t, what is the maximum possible of mu to recover without any distortion? Okay, so that's actually very easy to do. So this is part C. So remember, the condition to use an envelope detector condition. It was what? You have to make sure that once you add the envelope on top, you have to make sure that this is greater than 0. Okay? So if you took a look at what the original message signal was, you see that it was 1 plus 2 cosines, right? So what is the minimum value that this will ever reach? So what's going to happen is that you'll see a point where they're actually going to both become -1 and -1. So 1 subtract 1 subtract 1 will give you -1, right? So the minimum value of M of t would simply be -1. So what you'd have to do is you'd have to make sure that your carrier will make this situation above 0. So if the maximum value of M of t is -1, therefore you can simply make A equal to 1, right? Because that way what will happen is that it will be at the corner case where when you're doing the amplitude modulation, the most minimum part of that graph will just be just above the horizontal axis, and that's what you need to do in the envelope detector. So therefore, your modulation index would be the maximum peak divided by A. In this case, it's just 3 divided by 1, which is 3. So in this case, you can actually go above. It just depends on which signal you have. Okay? So this is to ensure that A plus M of t is bigger than or equal to 0. So that's actually possible there. Okay, actually I'll just skip the last one, that's fine. Okay, So there we go. Let me just double check the calculations here that I did for the power. So it's 1 squared c squared, 2 divided by 2. Yeah. So sorry, it's actually 2 squared. Let me just double check. So this is 2. So it's 1 and then a half 1 plus 2. Okay. That's fine. We'll leave it like that. That's fine. Okay. So that's the tutorial. So when you come back, we're going to finish off and take a look at some more amplitude modulation stuff, and we should be able to finish up the amplitude modulation theory today. And we'll talk about another topic in the next class, which is phase lock loops, which is synchronized demodulation. So we'll take a break, come back in 10 minutes, and then we'll finish off the theory.